Just before going to the second part, let me just give you a brief view what we have done in the past presentation. Okay. Uh, actually, so in the last part, what we have seen is we have seen this was the agenda for first part. Like we have seen the introduction to basic tools of and this low frequency side and its introduction to GUI part and what are the types of solvers available under the Maxwell tool, right? And after that, we try to design a permanent magnet synchronous machine in the last session, right? With the help of user-defined primitive models. Okay. So there we have seen the results also. Okay. So what I'm going to do in this part is that we will see the losses of a machine. Okay, so what I thought is like instead of going for the same machine and using the same machine for the results and all, I thought let's go for a different machine so that you'll be having a different view like what will happen with the other machines also. Okay, so, and yeah, one more important part is that for losses, eddy current and core losses part-wise, induction machines prefer a bit important part there. Like, see, in the induction machine rotor side, you have a squirrel cage part, right? Where meshing and all these parts are more important to get the correct results or we can say accurate results. Okay. So basically, mesh operations and all these things we'll be focusing today. One part is mesh operation part, and the second one is how the losses are going to affect by this meshing part. Okay, and how to calculate the losses and whether we can check for the proper thing or not, whether we are getting the input supply and output supply with output power, whether we are getting almost same or not. Okay, so these things you will see today. Okay. Uh, So what? Okay, let's go back to the our part two part session. Okay, yeah. So these are the losses which we can calculate under the Maxwell tool. Okay. So solid loss, standard loss, and standard loss are all these three comes under the copper loss category part, right? Which generally you can as simple as say you can say it's a I square R loss, right? But the way it is calculated in the Maxwell is like based on the current density and around the volume, or you can say uh, integration of a current density over a volume or over a surface, the way you are going to work on. Like if you are in a 3D geometry, you'll be working with a volume mode, and if you are in 2D, you will be working with a surface mode, right? So this is the way you will be calculating for solid and standard loss. But whereas in the standard loss R category, basically like when you are going for the voltage excitation, okay, so it is compulsory that we have to provide a series resistance to the excitation. Okay, so this resistance includes the winding resistance, and if you want to add any specific resistance to the supply source, that can be added here. Okay, so this resistance gives us the total, or you can say standard loss R when you are supplied the voltage excitation. Okay, so this is the thing which you have to remember, like when you are in a transient analysis mode. Okay, so like in the last session, we have seen the type of solver, right? Let me just go back to that. I think that would be better. Okay. Yeah, see, as you can see, there are seven types of solvers here, right? So when you are working on a machine analysis part, you have three types of solvers for magnetic mode. Okay, one is magnetostatic, eddy current, and transient analysis. Okay, so based on the type of excitation you are going to give, and you will be able to calculate inductance, resistance, and all these things. Okay, so whatever is the type of solver you are going to use here, either in all these three cases, Maxwell by default it can calculate the inductance of the winding. Okay, but whereas calculation of resistance is possible, or you can say it's done in the eddy current analysis only. Okay, only this solver has the feature to calculate the resistance directly. Okay, whereas magnetostatic and transient analysis solver, uh, for these things they will directly calculate the loss. instead of calculating the resistance of the winding, they will directly give you the solid loss if you have the solid conductor, or if you have the standard conductor. Conductor, you will be able to get the standard loss. Okay, so it will not give you resistance R. But if you are going for the transient analysis, sorry, if you're, in either of these cases, if you are giving the voltage excitation, so what will happen is you have to provide resistance in that, right? So the losses you will be able to calculate there is standard loss R, which is calculated through the current flowing through the winding as well as the resistance which is connected in series with the voltage source. Okay, so these are the bit important points which you have to keep in your mind while working with the losses part. Okay, and these things we have already seen. Okay, so coming to the core loss part, we have electrical steel and ferrite and hysteresis model. These three types of models are there. And apart from this, we have a power BP curve model also. Okay, so I'll show you that in the tool itself. I think that would be better. Okay, let me just start the tool. Yeah. If you notice here, this is the machine model which we have seen in the last webinar. Okay, this is the part one part. Okay, so where we have developed the geometry complete thing here. Okay, under this stator is this part, and permanent magnet, rotor, and coils, right? All these things. So this is under the magnetostatic. So that's the default part. So just to keep the geometry separately, we made this design, and then we have copied it to the. We made a copy of this, and we put it as for the transient analysis part. Right. So under the transient analysis part, we have assigned materials and as well as the as you can see here, regions are also added here. Right, vacuum band for motion setup. Okay, so all these things are added, including the excitations and all. Okay, mesh part, all these things you have seen. Okay, so right for today's part, what we are going to do is we'll be going to induction machine. Okay, so where what we will do is I'll just show you the dimensions and the machine rating and all. Okay, so the machine which we are going to work on today is induction machine, a three-phase induction machine. Okay. So you can see, I'll show you the these dimensions and all. Okay. What you need to do and all the changes also. Okay. What you have to do and all. Okay. So I've already, what you can say, made this design, okay, for time saving part, okay. So I'll just show you the properties. Like when you are going to create an RM expert model, what the steps is like, you have to go to here, okay, under the desktop tab. I hope you all know this how AEGT looks and how these two, we can say, where the options are and all, okay. So if you have any queries related to that, just let me know, okay, so that I'll go through it again, okay. So yeah, so under the desktop tab, you can see Maxwell, and you can just click on the RM expert part, okay. So once you click on this, uh, for the results, like if you are interested in seeing the results under the RM expert itself, so then select this option, generate RM expert solutions. If you are not interested in the results for the RM expert part, then you can go for the Maxwell model wizard. Okay. So now select this generate RM expert solution and go to standard mode. Okay. Or general also you can use for a three-phase induction motion. Motor. Specifically, see, general category means in the previous versions we had a machine called generic rotating machine. Okay, so by taking it out, what emphasis is done that it has created all the possible machines which are available under the market. Okay, in the market. So under the commutating machine we have two machines, and under synchronous machines we have these options, these type of machines. Under induction machines, these types of machines are available. Okay. In the industry, and these you can choose directly from here, or you can go to standard and you can choose a specific machine which you are working on, DC, AC, all these things. Okay. So right now we will be selecting under standard category and three-phase induction motor, and then once you click OK, it will automatically open this one. Okay. Uh, See this, with this procedure, you will just open a blank machine, like all the properties will not be there. Okay, or the values. Okay. So once the design is inserted here, just have to go to machine, and you have to enter the parameters like this. Okay. So the machine which we are going to design now is having two pole and it works with a 50 Hz frequency. Okay, and its power rating is 4 kilowatt mechanical power. So we are expecting that it should work at least for I mean, like its mechanical power will be 4 kilowatt. Okay, like torque into speed category part, we can say that. So rated speed is designed to be in between, like including the slip part, it should be in between 2900 to 2950. Okay, so reference speed will be 3000, right? For a synchronous speed is 3000. Obviously, if you have a two poles and 50 Hz frequency, right? 120 F by the formula. So 3000 RPM is synchronous speed, and rated speed of this induction machine, or you can say it will be in the range of 2900 to 2950 RPM. Okay, and it will automatically calculate. RM expert has the feasibility that it will automatically calculate to get the power, required output power. It will calculate the slip and it will calculate the speed range also, speed value also. Okay, so and voltage is 400 volts. That will be working. Okay, so you can see for now what we have considered is a frictional loss, and all these loss factors we have considered as zero. Okay. So if you want in your machine design based on your requirement, you can go for these losses also. Okay. So this is the first part on the machine, and let's go to stator part. So under the stator part, these are the diameters of the machine. Okay, outer diameter. Let me just check. Recording is happening. Yeah, it is there. Okay. So under the outer diameter, so these are the we can say dimensions of stator dimensions: outer diameter, and diameter, and length. Okay, stacking factor. Stacking factor is like we can say laminations, or how much percentage of the stator is laminated on all these things. Okay, and yeah, if you are going for the lamination sectors, like if you want to put calculate specifically that this many sectors are there, so that also you can do here. Okay, uh, or that is this default values we have used here, not changed anything much. Okay, and number of slots considered here are 18 slots, and 40 conductors per slot are used. So conductors are mentioned under the winding category. Okay, so slot type we have chosen is this one, semi-closed path. Okay, and okay, so these are the dimensions of stator, and now let's go to slot. So these are the slot dimensions. Okay, and yeah, okay. Now let's go to winding part. Okay, so under the winding part, you can see this is a single layer winding machine we have considered. Okay, and 40 conductors are there per slot, right? And winding type, like with how exactly the coils are connected, so that you can see whole coil. Okay, not short pitch or partial coil. And parallel branches, only one parallel branch is there. So like it's a single part thing. Okay, and number of strands, we are not considering any additional strands. Okay, and wire wrap, these are considered as default values, so that it will calculate if it is required. Okay, and wire size is given for diameter 1.369 mm. Okay, and coming to end or insulation part, all the values are given to the like zero, so that it will, if it is necessary, it will calculate automatically. Okay. Like when you are going for the industry point of like or application oriented design part, so in that case you have to calculate all these values specifically related to the machine application and its rating part. Okay. So based on that you have to calculate, and then you have to keep these values here. Okay. So for now, we're just keeping this as minimal as this, so that it will not take much time to simulate. Okay. So okay, now next part is under the rotor part. Okay. Under the rotor part, you can see again its dimensions, right? Number of slots, slot type. Okay. See under for the for this induction machine, rotor part is like cage rotor bar, right? So it will be having slots, and under these slots, all the rotor bars are shorted, right, with the end ring. So that we'll be selecting there. Okay. So here we are going to consider it as a single cage only, not as a double cage. If you are interested, then you can go for the double cage rotor also. Okay. Casting rotor and all these things. So we are not selecting this. So let's keep it as minimal as this. Okay. So the steel type we are considering it as a magnetic steel only. Okay. So M1924G for both stator and rotor parts. Okay. and these are the dimensions: outer dia, inner dia, and length. Okay. And coming to the winding part here, you can see aluminum rotor bars are used here, and end length and all these things you can see what are the thickness and all these things of these rotor bars, okay, and the end rings for both. What is the material used and all, and what type of shaft is used? Okay, non-magnetic shaft is used here. Okay, so these are the things, machine input. And coming to the setup part, you can see the rating of the machine and what type of load we are going to use and all. Okay, so this is a 4 kilowatt machine, right? So 4,000 watts are there rated output power, and rated voltage is 400 volts, and rated speed we are giving it as 2890. Okay, so I have mentioned 2900 to 2950, right? So okay, yeah, we can change it to 2900 also. Let's keep it as this. So let the RM expert do for our work. Okay. And coming to the frequency and winding connection, you can see here. Okay. So this is it, and click OK, and then we can just save this file. Okay. So once you save the file, you can directly right click here and validate. Okay. So once everything is fine, you can go for the analysis. Okay. So either you can right click on the design, analyze all, or you can go to simulation tab here. Validation also can be done here, and after that you can go for the analyze all. Okay, so it will analyze all the all the setups under this specific design which is highlighted. Okay, so either you can go here, or you can right click here and analyze all, or there is here also you can do. Okay, so there are several ways you can to run the analysis. Okay, just right click and analyze. So once it is done, it doesn't take much time. It will be taking a few seconds only. Okay. So once it is done, you can see the results under this results tab, or just right click on the results. Okay. So this is you can go for the solution data. Okay. So where you can see all the what will be its operating parameters, like you can say rated operations. Okay. The no load operation also we can see, and rated electrical data, right? And if you are and let's see the rated performance of the machine. Okay, so these are the rated parameters, and this is rated performance. Okay, so if you just I hope this is visible to you. Stator ohmic class is 170 watts. Okay, and rotor ohmic class are 97 watts, and iron core loss are is 103 watts, right? And frictional windage losses we have not given, so these losses are zero. Okay, and overall total losses are 371 loss. Okay, so this is the output power, almost 4,000 watts. Okay, and input power is 4,372. Okay. So efficiency coming is around 91.4981, and the power factor and all these things are calculated. Rated slip and rated speed, you can see 2928.47. So though we have given 2890, based on the rated power which is required, 4,000 watts or 4 kilowatts. Okay, it will automatically adjust the rated speed so that it will deliver the rated power. Okay. So rated torque is 13 Newton meter. Okay, and power factor also you can see 0.81. So this is fine. And if you are interested in seeing the curves also, you can see phase current versus speed, efficiency versus speed. So some of these curves are like torque versus output power. Okay, so like this, you can see some of the waveforms are plotted here. Okay, so you can see here. One is input current. So this one is the input current with respect to rotor speed. Okay, how it is changing, and this one is the power factor, how it is changing, and this one is the output torque. Okay, and torque versus speed, you can say. Okay, torque speed curve, and this one is the efficiency curve. Okay, so these are the results, and if you want any additional type of results, that can also be done. Like you can just right click and create RM expert report rectangular plot, and you can see what are the other options available parts. And if you want to calculate your own variables, then you can go for the output variables, and you can uh, use the category. Okay, and which type of variable you want to create, and then you can add that variable under the output variable category. Okay, and then you can plot that under the output variables part. Okay. So right now there is no variable here added. So once it is added, then you can plot it here. Okay. So this is it with the RM expert part. So once it is done, what we are going to do now is to further analyze the losses and how the losses will going to affect affected by the machine part and all. Okay. So what we are going to do is we will create a manual design from the RM expert. Okay. 2D design. Okay. So once 2D design is created, you can see this is how it's created. Okay. Instead of drawing, we are just using the RM expert to draw the complete machine. Okay. So here you can see automatically it has created the results also like torque, current, and that waveform. Okay. Results are not there. See, this is just a blank waveform. Okay. So So now what we are going to do is let's say so this is our machine, okay, and yeah, there are some one warning is there anti clearance, so it is not forwarded to this 2D design, okay. So I'll just clear the messages so that not get any confused. And that's all. Okay. So these are the things under aluminum category. We'll be seeing rotor bars. Okay. Under copper category, we'll be seeing the stator coils. Okay. So these are the coils. And under the material category, router and stator is there. And under the vacuum category, we have band, okay, which is assigned here under the model. Okay, motion setup is assigned, and so everything is assigned here only. Okay, we don't have to do anything. We just need to run the simulation and to see the results. Okay, so all the setups, excitations, boundaries, and all things are done. Inner region, outer region, shaft. Okay, all the things are done here. And you see here, boundaries are also assigned. Like last time we have discussed, right? Uh, we are going for the symmetry of symmetrical machine. We need to assign a dependent and independent boundaries such that it should understand that whether it is odd symmetry or even symmetry part, right? So this first one is the independent boundary because here we consider this the anti-clockwise direction, right? So, and this vector should be pointing outwards, radially outwards, and dependent boundary will be opposite to this. And see, you have two poles only, right? There is, so suppose this is a north pole, opposite one will be south pole, right? So obviously the values would be exactly opposite of it. So if you can see here, just take it. Dependent vector is dependent on this specific independent vector, okay? And the value of dependent flux density is equal to negative of the independent vector. Okay, so the pole is changing, so automatically the direction also it will be changing, right? And yeah, u vector direction we consider it as radially outward, so that's why it is selected as reverse. Okay, so this is it with the boundary and vector potential is there. Any question? Okay. So, and coming to the excitation, as you can see here, phase A winding and phase B, and sorry, this is phase B and this is phase C. So all three phases are there, and end connection for the rotor winding. Okay. So as you can see, rotor bars are shorter, right? So that for that purpose only we have given the end connection excitation here. As you can notice here, end connection winding is created like this. Okay. So end resistance between the adjacent conductors. So this resistance between the adjacent conductors, we are going to write this is the one calculated. Okay. So this is also given taken carry forward from the RM expert. So it calculates automatically the value and it provides it in here. Okay. The same way end inductance between the adjacent conductors. So this is the one. Okay. So when you are going for the circuit drawing, so double of this value will be coming. Okay. So this is with the end connection. And coming to the excitation part, this is the voltage excitation, initial current, and yeah, like I mentioned, if you are going for the voltage excitation, we have to provide a series resistance, right? So this is the series resistance, and the supply voltage, peak value, and this one. Okay. Okay, let's run the simulation and then we'll discuss a little bit more about it. Okay, so first, let me just change the name. Okay, so that we won't forget this part. First, what I'll do is I'm removing the mesh. Okay, so this is a no mesh design. Okay, so without any mesh operation, we will try to analyze the machine. Okay, so whatever are the meshes are created automatically. So I'm deleting all the meshes. So this means that see the mesh will be created, but only thing is that it follows the initial mesh setting. Okay, so let's see for this initial mesh setting, what will be the results we'll be getting. Okay, so let's run this file. Okay. Yeah. Before that, let's just change the setting of analysis part. Okay. Setup. And here we are increasing the time step also so that we can reduce the time of simulation. Also, we'll see how exactly it will affect the results also. Okay. So right now, we are running the simulation for 200 milliseconds and with a step time of 1 millisecond. Okay. So considering our frequency 50 hertz, we have a time period of 20 milliseconds, right? So for 20 milliseconds, we are considering time step as 1 millisecond. So it's like 20 points for a full wave, right? So in a way, it is fine basically. But if you're having more frequency or you can say more fluctuations inside of any particular waveform, so in that case, it would be a little bit less. Okay, we'll see that in the results. Okay, to understand that part. And the save fields, we are not saving any fields for now. Okay, and under advanced category, also not changing anything. Under the solver category, like if you are we'll just close this auto detect form. Okay, so that it will see generally what it does is auto detect. It will check the stop criterion 0.05 part under the any waveform. So once the waveform is almost in the settling state, like if it is repeating a certain behavior, it considers that the waveform or the system is in the steady state region. Okay, so there are no changes specific. So it will automatically stop the simulation. So that's the purpose of this auto detect part. So right now we don't want it. Okay. And fast switch is it helps you when you are using the voltage excitation part. Okay. So initial transients are there, right? So those initial transients which are not generally affect the machine performance. So those transients will be neglected during this voltage excitation part. Okay. So that we can uh, make it faster, the simulation time. Okay. So that's it with the setting. Okay. And then let's run the simulation and let's see how much time it will take. Okay. So meanwhile, if you have any queries till now, or if you miss any part, you can ask. Okay. So you can see there is a warning here. Currently, no mesh operation or data link have been created for the setup. Okay, so the initial mesh will be used. The initial mesh is usually not finite enough to achieve accurate solution. Okay, so this is the warning. So though it will give us the results, but it will not calculate the accurate solution. Okay, so let's see how exactly affects this in the solution. Okay, if we go here under the results tab, okay, so let's see the torque. Okay, so you can see how torque is changing. Okay, as you can notice, the average value is already calculated, but you might say that the value is coming in negative, right? That the reason for that is you have maximum value is available under the negative portion here. Okay. So when you are going to calculate average torque, you have to calculate under the steady state region part only. Like you have to choose at least from 100 after 100. Okay. So then only will be able to get the average torque here, or you can see this one, torque of the machine. Okay. So yeah, simulation is completed. It doesn't take much time. So now let's go to the um, yeah, let's see the currents here. Okay, so these are the currents you can see. It seems fine. Current waveform is fine because we took almost 20 points for each period, right? So it doesn't affect much. So induced voltage also, this is also fine. Okay, flux linkages, voltages. So voltages are purely sinusoidal. That's what we have given, right? And power. Yeah, let's come back to here. Here. So this is our main part which we have to focus here, right? So here, as you can see, here also average torque is negative. So let's just delete this one. Okay. Trace characteristics, clear all. So now I will just add trace characteristics all. I'll just choose the average, which is already selected here under my favorite range. So I'll just choose specified range. Okay. So as you can see, the value is almost settled after 100 milliseconds, right? So what I'll do, I will start from the 140 milliseconds. Okay. And specified start range is 140 and end range is 200. So it will calculate the uh, what you can say range, uh, average range is from this one. So in between this range only it will calculate the average value. Okay. So what what we can do? Okay, yeah, just click on the add trace. Okay, and now you can see it is in the positive value. Right now, close it. Okay, so now you can see the electrical power which is given as an input here is 4,700 watts approximately. Okay, and mechanical power is it's slightly higher than the 4,000 watts. Okay, so let's plot the uh, uh, losses also. Okay, so right click here and go for the modify report. Okay, so here under the category you can see loss, right? So under the loss, let's see, we have the number of more than one number of conductors, right? So standard loss we have to choose. Okay. So under standard loss also we are applying the voltage excitation, right? So for voltage excitation, we have to choose standard loss R because resistance is added there. So the loss which you have, the total loss, or I can say I square R loss will be calculated under the standard loss R. Okay. And right now we are interested in total copper loss, right? So obviously the rotor will also have the copper loss, right? It has sorry, not copper loss, variable loss. Okay. So I square R loss, you can say. Okay. So aluminum bar. So that those conductors are solid, right? So this will come under the solid loss category. Okay. So solid loss, I'll just copy this solid loss and standard loss R, add it and paste. Okay. So now you can see on the y-axis, I'm adding standard loss R. So this is the I square R loss of stator, and this is the solid loss. This is the I square R loss of rotor. Okay. And now I'll just add trace. Okay. So once I add the trace, it will automatically add one more axis. Okay. To this waveform. Okay. Right. So by default, it is creating by one axis here. Okay. So as you can see here, this is my y-axis for this part. Okay. So this one, right? And as you can see here, for left side y-axis, uh, the units are watts. Okay. But for the right side axis is by default units are calculated, so those are kilowatts. Okay. So let's change that. Okay. Double click. You will be able to see this one. So this one is the y2 axis. Okay. Right side one. So select this y2 scaling. Okay. And you can see units are kilowatts. So change it to watts and watts. Okay. Apply. Okay. So now we can see this what units are almost both are in the same range. Okay. So now let's calculate it. Okay. Let's see what is the error here. Okay. So if you see here, this is our electrical power, 4,713. Okay. But whereas if you calculate the mechanical power, okay, output power, uh, uh, including the losses, how much we are able to get. Okay. 4, 4, 65.9, right? So this is the electric mechanical power plus loss is 319.4. Okay. So as you can see, this is slightly ahead of electrical power. Okay. So in a way, if you calculate, your output power is slightly higher than the input power, right? So this not possible, right? So the reason for this is, though the error is small, but the reason for this is we have not assigned any mesh operation here, right? So because of that, we get this type of result. Okay. So now let's go back here. Okay, back to the this part design. Okay, and what I'll do, I'll copy this design and paste. Okay, so now I have a third design. Okay, I'll just rename it to width mesh. Okay, So now what I'll do in this, I'll assign the mesh operation now. Okay. So as you can notice here, though under the second part we have deleted all the mesh operations. Uh, the moment we copy it, automatically one mesh category is added here. Okay, so that is because of motion setup. Cylindrical gap treatment will be added automatically in the latest versions of ANSYS. Okay, so user doesn't have to add it. Automatically it will add. Okay, so that air gap treatment will be created automatically. Okay, meshing operation. So additional thing what we do right now is we are not going to assign any mesh operation for stator or stator coil or rotor. Okay, so the most important part which affects the induction machine or eddy currents or these things is rotor bar current. Okay, so that's the important part for which affects mostly on the ripples of torque and all these things. Okay, so as you can see, as you have noticed here, torque. Sorry, not this one. Previous result. Okay. Uh, yeah. See, there are ripples are there. Okay, and also under the powers also, if I just zoom it here. Okay. Let me just zoom a specific area. Right. So, right. So as you can see, there is no like you can say periodicity is not there, but the ripples are there. Right. So these things we can reduce by assigning the mesh part. Okay. So what we will do, we will assign the mesh operation for the rotor bars. Okay. Only rotor bars, which affects generally much. Okay. So select the bar, shift, and last one, right click, assign mesh operation, insert selection, length paste. Okay. So here what I'll do is I'll change the under the length, sorry, inside element mesh operation, length based part. We have two options. One is either you can choose maximum element length. Okay. And second option is maximum number of additional elements. Okay. So either you can choose number of elements or number of triangles you are going to create, or you can choose maximum element length. So each what will be the element maximum element length that you can choose in the triangle. Okay. So by default it is given as 3.2 mm. So I'll make it 1 mm. Okay. And then click OK. So now length bar is added. Okay. So yeah. So to show you the difference between the meshes in second initial mesh setting and after this part, we'll compare the mesh part. Okay. So before analyzing this one, let's plot the mesh. Okay. So let's generate the mesh part. Right click on the analysis and generate the mesh. So this is with the mesh path. Okay. Yeah, mesh is generated. Yeah, mesh is generated. And for a second design also, I will plot the mesh. Okay, so here the simulation is completed. So I can directly plot the mesh here. Okay, Control A, right click, so plot mesh. Okay, and uh, yeah, so Control D. So now you can see the complete machine here. Okay, so if I zoom in here, so this is with a no mesh, like with a basic, you can say. Uh, uh, Initial mesh settings part. Okay, so where you can see the mesh which is generated under the rotor bar is less density. Like size of the triangle element is little bit bigger here. Okay, so now let's check the mesh design where we have assigned the mesh, right. One element, 1 mm is the maximum element length, right. So now let's go here and we have already designed, generated the mesh for this one, right. So now I'll select again here, Control A, right click, uh, plot mesh, and done. Okay. So now you can see, just let me just zoom in. Okay. So if you notice here, the number of triangles inside the rotor bar are changed. It's increased. Okay, a lot. So based on this, you can see there is a difference between the meshing, right? And and now let's see how exactly this meshing meshing part affects our result. Okay. So just hide it. Okay. Now let's analyze this. Yeah. And also let's change the time step also. Okay. Because time step also affects a little bit. So let's increase it to the old part like 0.2 milliseconds. Okay, so that we can cover and let's see solver. This is there. Okay, yeah. Uh, yeah. See under the result here, as you can see, this difference. So this is between 21 millisecond, right? So in between 1 millisecond also, what if there is any change that we will notice in the next model. Okay, so let's go back here, 200 milliseconds, 0.2 millisecond, and save fields. We are not saving any field right now, right? To save the simulation time, okay, to make it faster, right? So let's start the simulation. This one, okay, validation is fine. Now analyze, okay. So this is third mesh design, okay. So you can see once the simulation is completed, you will see the message under this one, message manager, okay. Motion setup also you can see what is the data we have given here. Okay, it's the 2928, which is the value the calculated under the RM expert part. Okay, so we can see the results also. Okay, start for 10 milliseconds. So right now 10 milliseconds are completed, and coming to power also you can see going on. So the losses we have already added here. Standard loss plus solid loss. Okay. So once the simulation is completed, then you will be able to see the average value. Okay. And let's see, you can see the difference also here. There are so many variations, or you can say changes with the time step. Okay, the reduction in the time step. Okay, let's yeah, let's calculate the previous part. Like in this no mesh part, we have seen the results. Start. Yeah, let's go to power here. Okay, so the calculator gave us the values of this one. So total power is output power, you can say, adding like the input power is 4713 and output power is this. So let's minus this one. Okay, minus 4713, right? 4713.2 approximately. So this is a 72 hours difference. We just divide it with the input electrical power, which is 4713. Okay, so we'll get a into 100, we'll get a 1.5 percentage error approximately, right? So this is the error we are getting. Like if you are considering the 100% efficiency, or if like sorry, 100% accurate result. So in that case, you can see 1.5 percentage error is there. Okay, so this is on the positive, sorry, negative side, you can say, because the power is more than that after adding the losses, right? So now let's check the same thing for after assigning the mesh part. Okay, we could have stopped it after 140 itself, I think. Almost same. So it is not taking much time. And let's compare the timing also, because we have increased the uh, time step, right? So let's see the solution data of the previous one and see how much time it took to calculate the simulation. Okay, solution process, elapsed time. So it is started at 3:30, 30 seconds, and end time is 3:31 1. So it's approximately took 1 minute 10 seconds. Okay. can say after combining it with 3 seconds, so 1.5 minutes you can consider, okay, approximately. For this, it is taking a little bit more than that. Okay, you can check from here also. It started at 3:30 and ended at 3:31. Okay. The same way we will see the timing from here also. Like we can go to here for the same thing. Result, result, solution data. So the simulation, yeah, we won't be able to see it properly because here the simulation is going on. Okay. Yeah, it is almost done. Final solution process. Once it is done, it saves the result and done. It will be closing. Okay. So now also you can see simulation ended at 3:49, and you can see it started around 3:40. So it took almost 9 minutes. Okay. So just we have increased the time step uh, by how much you can say. Sorry, time step is reduced. Number of steps are increased. Okay. So time step is reduced from 1 milliseconds to 0.2 milliseconds. So 5 times we have reduced. Okay. Uh, So because of that, the time to simulate the complete model is increased, right? So now it took almost 9 minutes, 9.5 minutes. Okay, so that option that you can see from here also. Okay, 349. Okay. So now let's see. Let's just zoom this, and you can see how the torque waveform is changing. Okay. So in this case, I think you can see there is a periodicity here, or not sure. Okay, let me just zoom in again. So, without sorry. Okay. So now I think you can see how the changes are there. Okay. So same way, if you have seen there, we only see changes are a bit bigger, right? Because there the difference is 1 millisecond. Now we have so many points between 1 millisecond, 5 points, 5 additional points, and 1 millisecond, right? So because of that, you can see that small change also here. Okay, in the waveform. And for torque also, you can see the same part. Okay. So now let's see. Let's check the uh, losses calculation. Okay, so how the values are going to change here because of the meshing and this time step part. Okay, so our electrical power is 4716, right? And mechanical power calculated now is 4366. Okay, 4366.3 plus 336.4. Okay, now it is 4702. Okay, so if I just minus, so now you can see the values. So it's almost realistic because the input power, electrical power, is higher than the mechanical power plus this uh, I square R losses. Okay, in a way, I can say variable losses, right? So which is a little bit lower than that. So you can say the difference is almost 14, right? Yeah, approximately 14. So just minus it, 4716.8. Okay, so this is minus 14.1. Okay, so 14.1. So additional losses are there, which may be because of core losses. Okay, and yeah, right now we have not considered this constant losses, core losses, or eddy current losses. So all these constant losses we have avoided right now. Okay, so this is gone somewhere. So if you just divided this 14 divided by 4716. Okay, 14 divided by 4716. Okay. So you will get a 2% error. Sorry, 0.2% error. So previously the error was 1.5%. Now you have the error 0.2 now, okay, 0.3%, which is fine, okay. And yeah, let's change something, okay, which again there are some things which we can check and analyze, okay. Like, see, if you want to see, like I have mentioned that in the previous part, no mesh there, we have not, there is rotor bar current affects much, right? So that's what I have mentioned. Like, so let's see the rotor bar current. Okay. So here you can see end winding, right? So under the end connection, you can see current under the end connection one. Okay. So this one we can plot. So new report. Okay. So this is the current which you can see here, right? Under this without mesh part. Okay. So how exactly this is changing? So now let's plot the same waveform under this part. Okay, create transient report, rectangular plot, end connection, current end connection, new report. Okay, see the difference. Now you can clearly see there is a periodicity and how exactly the rotor current is changing inside of it. Okay, like with small or minor changes also. Okay, included. So this is the part which I want to show you all the losses. So you might be wondering, like we have only considered right now for variable losses, or you can say the losses because of the resistance only. Okay. So we have completely neglected for now is the constant losses or core losses and all. Okay. So now let's add the core losses also. Okay. So for adding the core losses, what we need to do is we need to go to the excitations and right click and assign core loss. Okay, so set core loss. So we have set ADFX also, option is also there. But ADFX, like if you are interested in only ADFX, AD current and ADFX, then you can go for the set ADFX. If you want complete core loss, core loss automatically includes this ADFX, hysteresis, for additional extra losses also. Okay, so all the constant losses will be added under the core losses. Okay, so if you are going for core loss, then there is no need of assigning set any effect. Okay, so we can go to set core loss, and here by material property, okay, stator and rotor, right? Stator and rotor are the defined materials for the core loss setting. Okay, so only these two can be selected here. Okay, stator as well as rotor, only these two materials. Okay, so if you want to see, right now I'm not assigning it. Let's make a new model here. Okay, I'll just copy it, save, and copy this design, paste it here. Okay, so now I'll just change the name. So now I'm going for the core loss. Okay, so here for the change, what I'm going to do now is I'll assign the core loss. Okay, for the stator and rotor. So before that, let me just show you how exactly the core loss will be calculated. Okay, so I'll show you under the material property itself instead of presentation part. I feel this is the a better way. Okay, so let's go to properties of the material. Okay, so if you open the material library, there itself we can see what type of core loss model we are going to calculate. Okay, yeah. So this is the material which we are using now. Okay, so let's go to view or edit material properties. So you can see here, this is the pH curve of this material. Okay, magnetic steel, right? And we are not changing anything under here. If you see here, uh, I hope this is visible to you all. Under the core loss model, we have it is selected as electrical steel. So we have power ferrite, BP curve. Okay, hysteresis is not there here for this. Okay, uh, so electrical steel model is there. So for electrical steel type of core loss model, we'll be having the type of empirical formula which we use is available already. Uh, okay, I have not shown you that. Okay, so which you can find out in a published paper also, IEEE journal paper. Okay, which I'll share it later on. Okay, so where these constants will be there. H is for KH is for hysteresis loss constant, okay, and C is the eddy current loss constant, and E is the excessive loss constant, okay. So these three loss constants will be there, and this will be products of uh, flux density and frequency, okay. So in relation, so these constants will be calculated for or given for this material, okay. So with these values, it will be calculated the core loss, okay. So, though the calculation of core loss in simulation world is bit tricky because see when you are calculating the core loss in the real time world, it always it affects sorry it gets affected because of demagnetization or by the age of the material, right? Or we can say, sorry, magnetic saturation part, force saturation, all these things, okay? And the temperature of the working condition of the machine, okay? So these real-time scenarios includes all these parts, which changes the core loss value which we have calculated through the simulation, okay? So when a design engineer is working on a real-time part, so after considering all these parts, we can expect a minimum of 30 percentage change in the core loss calculation when you are comparing with the simulation part. Okay, so this is quite normal. Okay, so but still we can make it possible to reduce the error here. Okay, so let's see. Let's add the core loss here. Okay, so under the core loss, we have two options. One is speed. Let's just assign the core loss first, and then I'll tell you what are those two options. Okay, so set core loss here. Okay, so now select the stator and rotor. Okay, so core loss is selected now. And yeah, if you notice here, there is a one more tab here, advanced tab. Okay, so basically, if you select stator and rotor here for core loss setting, it will calculate the core loss, but it doesn't add it to the total power balance equation. Okay, so as you have noticed in the previous design, okay. Any question? Any question? So yeah, so we were previously saying that rotor and stator we have added here. So it will calculate the core loss on the stator and rotor overall. Okay, but the thing is that it will not add this core loss value, core power loss, to the power balance equation. Power balance equation means like electrical power equal to mechanical power plus total losses, right? So total loss includes like I square or you can say variable loss plus or constant loss, right? So this constant loss is not will not be added here unless if you choose this button, okay, this option, core loss effect on the field. So if you select this option, then only this core loss will be included in the power balance equation. Okay. So it's up to the user whether the user wants to just calculate the core loss or whether the user is interested in adding this to the power balance equation and all. Okay. First, let's calculate the core loss itself. Okay. And let's see how exactly it differs. Okay. Whether it is exactly not matching to the power balance and all. That also I will show you. Okay. So stator part and the rotor part here, okay. And now click OK. So right now we are not selecting this option, okay. So now let's see the results, how exactly it changes, okay. So now core loss setting is done, right? Just cross verify. Yeah, stator, rotor, yeah, done, okay. So now I will run the simulation again, okay. And yeah, to reduce the simulation time, right now it took almost 9 minutes to solve, right? So what I'll do, we have a separate setting actually, okay. Like we can always go, right? So in the simulation setting, if you see under the results part, the previous results, okay, here, okay, up to here or up to 120 or 100 milliseconds or 140 milliseconds, these changes are not much. Okay, so these are not much required for us. After this, we will be needing less time step. Okay, so after settling these values, okay. So what we will do is up to 140 or 150 milliseconds, we will use the different step time, and after this, we will go for the different step time. Okay, so that we can reduce the simulation time. Okay, and yeah, let's go to setup here of a core loss design part. Okay, So here, instead of writing the time step, I'll write an if condition. Okay, if uh, brackets we have to open, if uh, the condition is like time is less than. Okay, so here it is in the seconds always. Okay, so you have to write 140 milliseconds means 0.14. Okay, syntax is like if time less than 0.14 seconds, comma, if the condition is true, your time constant will be, sorry, step time will be 1 millisecond. Okay, so this is 1 millisecond. And if it is not satisfying the condition, like if it is more than the 140 milliseconds, then my time step will be 0.0002. Okay, so this means 0.2 milliseconds. Okay, so now close the bracket. So now this is the condition which we are going to do. So up to 140 milliseconds, uh, yeah, time step will be 1 millisecond. After 140 milliseconds, time step will be 0.2 milliseconds. Okay, so let's fit this. Okay, and if you want to see the fields also, we can choose the field. But again, once we are going to save the field, automatically it increases the time of simulation. Okay, so right now let's just save the simulation as it is. Okay, not going to save the field. Okay, so rest of the things are normal. Or if you are going for the more accuracy of the results, then right now under the solver category, nonlinear residual is 1 into 10 power minus 4. Okay. So if you are going for the more accurate results in this in all the waveforms, so you can reduce this value to 1 into 10 power minus 7 minus 8 like that. Okay. So the more you reduce this value or more you keep it as near to the zero, the more accurate value you will get here. Okay. So this is right now I'm not going to change it. Okay, since it consumes a lot of time. Okay, so let's keep it for only this part. Okay, and click OK. So now our step time is changed, right? And core loss is added. Yeah, core loss is added. So sorry, we have to select for both design, right? So just verify set core loss, yes, and setup, yes, done. Now I'll just run this one. Okay, analyze all. So now let's see how much time it will take because we have changed the step time, right? So we can see the results also in a similar way. Okay. As you can see, yeah, also the current also. Okay. So in chart, same way for power. Okay. And you can notice here how exactly it is changing. So now you can see the change in the second time is 1 millisecond. Okay. Up to 60 milliseconds, it is going faster. The simulation is faster. So once it reaches the 140 milliseconds, it becomes a little bit slow because the number of what you can say the time step is reduced. Right? See the mesh is there. Okay. So now you can see from 140 milliseconds time step is changed, and you can see how it is changing. Okay. Now, yeah, while it is simulating, let's add the core loss also here. Okay. So modify the report and go to loss section under the category and here core loss. So if you want to calculate individual core loss of rotor and stator like this, we can add. Otherwise, I'll be calculating the total core loss. So I'll just add the core loss here. Okay, add trace and close. Okay. So now I have four waveforms here. Okay, electrical power, mechanical power, standard loss, this constant variable loss, and the constant loss. Okay. It's almost done. Yeah, it is done. So you can cross verify now. The time time of simulation. Okay. So let's say here time of simulation is let's see go to the result and solution data, and simulation is completed at 4:10, and we have started the simulation around 4:05. Okay. So it is only 3 minutes. So we have reduced the simulation time from 9 minutes to 3 minutes by just changing the step time. Okay. Though the calculation of core loss is added additionally, but it doesn't affect much because we have not added this to the power balance equation. Like so, again, once we add the core loss to the power balance equation, then it will take a little bit of more time. Okay, so now it took around 3 to 4 minutes, right? Half of the time we have reduced by adding this part, right? So let's see the power balance part, like how exactly it is seen. Okay, it is calculator on the calculator. Yeah. Now let's calculate the total power. So total power we are getting electrically is 4768 and mechanically is 4411. So 4411 point 7 plus 342.5 plus 91.43. Okay, we can keep it as 4 itself. Okay. So this is 4845. So again, now you can see the error is little. So because the core loss is calculated right now, but it is not adding to the power balance equation, because if you add it to the power balance equation, your output power is not matching to the input power. Sorry, output power plus losses is not is more than the input power. Right? It is almost 80. Right? So if I just minus it with the 4768, you will see 77 watts. Okay. So this is the difference you can see because of the core loss. Okay. So let's add it to the power balance and how it will affect the fields and all. Okay. And we'll see how much time it will take the simulation and how it will affect you. So right now, just remember the difference is okay, I'll close this. Okay, fine. 70 approximately, right? So let's just set core loss and go to advanced. Consider loss effect on field. Okay. Now click OK. Now you can see the waveform. These results are being cancelled. Okay. So now again I will analyze it. Right. See, now we have added to the field loss, right? So it will take a little bit of more time when compared to the previous one. Okay. So we have started the simulation around 4:10, right? So now let's see how much time it will take. Okay, for completing the simulation. Previously it took almost 4 minutes, right? 3 or 4 minutes. See, every time you can notice there is a difference in the waveform, like when we are changing the step time. Okay. So right now we have not changed the step time. So previous waveform and this waveform will be almost same. But yeah, the difference here because we can notice is because of the core loss is added to this field. Okay. So meanwhile, any questions like related to the previous part or a present part? So core loss value is almost same, 91 watts only. But thing what we need to check is whether it is going to be added in the power balance or not. Okay. So till now, if you have any queries, you can ask. This is up to this part only. I wanted to show you on this loss calculations and all. Okay, for a machine part. Okay. So this is the same, like it's the same part. Like when if you are working on any machine, meshing is important. Okay, and second thing is core loss, like type whether you are interested in core loss or not, and how to calculate the how to check the standard loss and all. Okay, so these things are important. Okay, like yeah, there are other options also if you are interested in calculating the core loss or current through the conductors and all. Like these things can be done through the field calculator also, but for that you need to save the fields first. Okay. So what we need to do, like for example, if you are going for the field, like under the analysis part here, sorry, just double click, uh, save field, like see, once we save the field for a custom stage or any different specific time, okay, so then we can go to field calculator, okay, here, field calculator. Through this, we can calculate, see, right now it is already calculated, the core loss, total loss, all. Okay. Suppose if you want to calculate the current density or current flowing to the specific rotor bar, okay, that you can calculate here, which is given already under the result, but you can cross verify. Okay. What you need to do is you need to select the current density and its scalar dimension. Okay, this is along the z-axis, so you have to choose the z-axis, and then you'll be going to geometry here. Okay, so under the geometry, this is 2D, right? So we'll go into surface and we'll be selecting any bar. Okay, one bar. And then, so every time you have to click, then it will be added here. Okay. So right now fields are not added, fields are not saved here. So that's why I'm not adding it here. Okay. And once it is done, volumetric, then you will be selecting the integrate option. Okay. So integrate over this particular surface. Then you can click on the evaluate option. Okay. So then you will be getting the results. Or you can just plot the waveform also. Okay. So this the variable which we have created through the field calculator will be available under the calculator expression. So if you go here, you'll be able to see expression catchy here. Okay, so under this, sorry, calculator expressions, there is one more option. Output variable and the connection we have. Okay, right now it is not there because we have not saved the field. Okay, so once the fields are saved, then you will be able to get the here one more option, calculator expression. So from that, you will be able to see those variables. Okay, to plot. Okay. Oh, sorry. Not, from here, you will be able to calculate rate. Under the fields report, these are the fields, right? So from here, right now there are no expressions, so you won't be able to. So the simulation is completed. Let's see how much time it is again. Previously it was 2 minutes, right? Sorry, 3 or 4 minutes. I'm sure. Let's check. It's completed around 4:15, and yeah. So now you can see it's almost 10 minutes. Sorry, 5 minutes. Started at 4:10, right? So it's the same design. So that's why both the calculations are there here. Okay, so the second simulation is in between around somewhere here. Okay, you have to search for it. But you can check here. It started around 4:10:39 and completed around 4:15:49. So almost 5 minutes. So previously it was three minutes, 3.5 minutes. Now it is increased to 5 minutes. Okay. So now let's see the results and how exactly this is affecting the power balance curve. Okay. So let's go to the calculator and it's 4390.9 plus 346.6 plus 93.5. So this is 4831. So and the electrical power which we are getting now here is minus 4814.5. Okay. So this is 16. Okay. So previously, when we have not added this core loss to the power balance equation, 70 was the difference. Now you can see the 16 watts is the difference. So if you just divide the 16 with the 4814, okay, 4814, then approximately you will get 3% error. Okay. So 3% error in the simulation is it's fine. I think it's acceptable. Right? Sorry, not 3, 0.3%. Sorry, into 100, right? So 0.3. So 0.3 seems acceptable. I think so. So any questions still now from your side? Any queries, or if you want to know anything specific part for this machine design or